Hello everyone. Good morning. And my name is Prashant, and I'm ESR7. Currently, I'm at Tampere University, and previously I have been to VC. And today I will be basically spending about ego velocity estimation with automotive radars, high resolution radar, and we'll go here. So the agenda for this stay here. So basically, we will just go through a brief background and then the radar data processing, then what is we are doing in this work, and then our proposed method, and like what data set we used, and pre-processing, and experiments and results. So we'll start with the background. So basically, my research topics is mapping and localization in GNSS denied environments. And basically, if we want to do that, we try to learn what are the static objects in the environment, what are the dynamic objects, and their position in the real space with respect to the machine and in the global map. Also, if we have already a map, so we basically estimating the position of the robot in that map. So that's basically localization. And if you don't have map, or you don't have poses, then you do SLAM, which is basically simultaneously estimating the pose of the machine and mapping the what is around. So, and also there is odometry or Egomotion estimation. So you will basically track the pose, like how much you moved from your previous position. And this is the general architecture of the SLAM system, which has front end. My work basically fall in the front end area, where we have the sensing. We use LiDAR, radar, camera, of course, IMU. And then we do feature extraction. So this feature extraction is basically, you try to identify the static and stable landmarks, which you can use for further data association to estimate how much you moved, or estimating the pose, or doing place recognition. And then that can be formed with this backend, in a global map. So we will go next. So basically, yeah. So what are the challenges with these things? I think you have seen the presentation from Himanshu. He is also working on extreme weather conditions, which is usually a problem when you use optical sensors like LiDAR and camera. And they also face challenges in adverse visibility, which is usual cases for the heavy duty machine industry, and these kind of conditions. So basically, what we can look for, other perception modalities like radars. And so my work is basically, it's related with the radars. I'm exploring the use of automotive radars in this solving the mapping and localization task, or odometry estimation. And this work we will basically we are doing the ego velocity estimation using the radar data. So this is a typical automotive radar, which is a high resolution radar, the new generation. So it has it can give you 4-dimensional data, which has range, azimuth, horizontal angle, and elevation, the height of the objects, and the Doppler. Per reflection, it will also give you the Doppler velocity with relative to the sensor. And it has more antennas, more channels, which will help to get better angular resolution, which is always a case for radars. The current radars being used in automotive industry, they are usually not that high resolution. But now they are more there is more interest in developing high resolution radars. And how a typical high resolution radar look like? So roughly the azimuth resolution. So basically in horizontal plane, the difference between two detected points should be less than 1 degree. So it can differentiate between those. And then in elevation, it's the difference between 2 points could be 15 degree. And of course, the range resolution, the difference between the range of 2 detected points. And these sensors work in 77 to 81 gigahertz frequency modulated way, so it can like sweep the a decent area in front of the sensors and like detect the objects or other things. And how they stands with comparison of other sensors, we have like basically these points, and this image is like basically our current setup which we are using like to collect data. And so it has camera, radar, and like it's a hand carry rig. And in the table this the comparison, so we can see like in bad visibility, radar has like better chances of perceiving the environment than other sensors. Of course there are other problems with radar, like they are still not that mature and like a bit expensive, especially the high resolution radar. So if we see like how the data processing pipeline look for a radar, because they are kind of they works in radio wave range, and they collect the data they collect in first stage that looks like something on the right side. Yeah, so this like this, and then we run the set of Fourier transforms. So like which the first stage we estimate the range, then the Doppler, and then we have like range Doppler map for each channel, and after that we do the angle processing, so we get a volumetric representation of that data. So it has angle like both. Okay, sorry, just so basically like yeah, this was this is how the it looks like. It has elevation dimension, azimuth, and the range, and this color plot shows the reflection intensity from each point in the space. And after that, like there is the CFAR, the constant false alarm. There are different variants which used to threshold, because the radar perceive they get reflection from everything in their way, even from the ground. So to find the object or like point of interest, you need to threshold the data above certain intensity, and the data it looks like something like this, the point, and that's so-called like point cloud for radar. So majority of like available radar methods which use this, they look like this data, and they're more into this one. But we are more like interested in the previous stage, because when you do this processing, you lose a lot of data which might be important, because it's like just a filtering, and you are just without like any, you just put some dynamic threshold or like some fixed threshold, and you filter out less than. There might be a case like if there are small objects, so you will be missing them. So that's why we decided to use like even this like range azimuth elevation heat map. And in this work, basically we are doing like ego velocity using this data. So basically what is the ego velocity? So for the ego vehicle where the sensor is mounted, the estimating like when it moves, estimating the motion, like how much the change has been in the transformation, basically like it's like pose in rotation and translation. And basically in radar's case, in this kind of radar, it can be done in two ways. The first one is basically the Doppler based single scan. So you just need one scan, and you can get like for each point you will get the Doppler velocity, and you will try to find this platform's velocity. But the problem with that is like you can either do all linear, like x, y, g, the linear ego velocity, or you can do like 2D full ego motion, which include the like x, y translation and heading estimation. So we decided to use basically the like multi-frame, like consecutive frame-based method, and it's learning-based. So it has a set of network. So the first part is basically the 3D convolution neural network based feature extractor, and then we have the transformer encoder and two head for like predicting the linear ego velocity and the angular ego velocity. So, and we named it like 4D ego. So we are, as I explained, like we are using the consecutive scan and trying to like use the features in those scan to like these high intensity features and to basically predict the linear and angular ego velocity. And I saw you in the data processing stage, like what we got that volumetric data, and that was in the polar format there. So it means like it has a spherical coordinate system where the azimuth was in angle and elevation, and then there was range. So we converted then that first to the Cartesian, and all the values were like x, y, g basically, and the intensity, we didn't use Doppler in this, just the intensity of the the scan. And then we have used the like CNN feature extractor, which find like basically the high intensity regions, and then a transformer layer, because it's a sequence, we are feeding like a set of consecutive pairs, so find like the changes in those features, and based on that, like we have this linear layers which predicts 6 degree of freedom eco velocity. And this is our network basically look like. So like each of the this scan pair, it's like 32 by 128 by 128. So 32 is basically the elevation, 128 is like the number of range bins, and then the azimuth. So we concatenate them together, and then we feed it to our feature extractor, which is a 9-layer 3D CNN network. And then we flatten and we feed to the transformer block. And then we like basically get this two set of values. Our loss function was basically weighted Euclidean distance. So you have the predicted velocity vectors and the ground truth velocity vectors. You try to fit your model with respect to this. And the weight were basically to balance the training, because the notation were different. The angles were like in degree, angular velocity were degree per second, and it was very small quantities in comparison of linear velocity. So we kind of use the weight just to balance the training. And basically like we use 3D CNN because our data was 3D, the volumetric, and this network was basically inspired from the FlowNet, which has been popularly used to learn the optical flow from a pair of camera images. And it has been also applied to LiDAR and other work before this with the radar. And then like the transformer encoder, basically it was something if you have it basically like find the purpose of using transformer is like you will only focus on like the regions which are contributing to the egomotion, the features, and they are like local context and the global context in the scan. And it's been not applying directly on the scan, but in the latent space, the feature we get from the scans. So we are applying there. And this was the data set we used for training, because there was like, this sensor was a bit tricky, so it's hard to collect own data yet. Like we kind of developed the software stack, so now we can probably use these methods real time. But we got this Coloradar data set, which we're using the same sensor. And it has like other modalities as well, like for ground truth LiDAR, IMU. And then they have the ground truth POJ, has been generated by a LiDAR inertial SLAM. And then they had like 57 sequences, like the duration was like 1 to 3 minutes. And they had 6 different kind of environment, where structure buildings and nighttime, outdoor, and tunnel were also there. And each sequence has the relative pose with respect to the initial position, like where the sequence is starting. And the one benefit was they had also the raw data, raw 4D data, which we are interested and working on. So basically for the training, the pose was given in a transformation matrix format, like 4 by 4 matrix. And we use this twist calculation formula basically to find the linear velocity components and this matrix which will give us the angular velocity using the time derivative of the transformation matrix. So there was the time difference because our sensor was like the data we were getting in this data set were 5 frames per second. So roughly between like 2 scans, the difference was like 0.2 second. And yeah, so this was our like pre-processing stage. So our experiment was like basically there were 4 sets, and we had like the proposed idea, which has the transformer encoder and fully connected layer, and then we had other variants of attention, which were channel attention and then self attention. Self attention was basically there was a previous work milli-ego. But the thing was like they were using the IMU also with the radar. It was not radar only method, but we used the radar subnet. So it's basically this network was just a modification with the 3D CNN or the same network which we compared. So we had these 4 variants of network, and our evaluation matrix was root mean square error between the predicted and the ground truth values. And then we made like different set of training and testing data. So the mixed data was basically it include the indoor and outdoor data. And then we also did like we trained on that. We tested on like mixed data, and we trained on like only indoor data, tested on outdoor, those kind of things. And also like we did on the trajectory, like only stationary part also we did the comparison, and moving part also. So also like there was this low speed and high speed. The thing was like that data set was collected with a hand carried rig, like a person walking with the sensors and collecting data. And there were some sequences they used electric skateboard. So basically it was not that high speed, but it's still like, but the majority of data was with the walking sensor rig. And this was the like result we basically got for 4 different sequences. They're outdoor, and we can see like basically this all the ego velocity components, and this root mean square errors. And then we had like this 4 sequences or 4 network. So we can see clearly in most of the cases transformer was doing well, and like in some cases it didn't that, but most of the cases like because if we see the problem was like this omega x and omega y were not that significant. The omega g was heading, it was a bit where like the values were varying a bit larger extent than other components. So that was one reason. And then this was basically the error plot for those errors which we saw in the tables. And it's the box plot basically, which the blue bar shows the error distribution, and the line shows basically the median, and this triangle is the mean. So it's for all the models, each velocity components we did the comparison. Then there are like these plots for one sequence, which were like the blue line is the ground truth, and the red is the predicted velocity, and it's like forward velocity, which was Vy, and then this was heading omega g, and there is this Vx, which might be the side slip velocity. So this was the thing, and the conclusion we have basically. So with this, like we can learn the ego motion from the radar data, and then the other thing was like we didn't use point data, and also we kind of avoided like heavy processing, because this CFAR processing is basically is a bit expensive, and also you lose a lot of data. So that was one thing. And then we we also saw like using the attention heads in the network improve the results, which clearly show our transformer encoder model. And then the one thing was like it has been trained with the motion ground truth. So if you have trained the model in like low speed data and you're trying to use it in high speed, then it won't work that well. So it's kind of supervised. And so yeah, that one was basically these 3 points I concluded from this work. And now currently we are using the same like the Egomotion to learn the stable features, because in previous work we basically learned those features in latent space, but now we are trying to reconstruct those features so we can have like these landmarks in the environment, basically with the less noise. So that's an ongoing work. And also like we have planned to use this Doppler at some point, which will help us to classify the objects and like also doing like the detection of objects. So this was from our paper, which was published in this summer. Yeah, that's it. This is, I mean, I believe.